Hello everyone. This lecture series is going to be about hydrotherapy and fluidotherapy. This will all be in one, actually there are two Word documents or two lecture outlines, a separate one for hydrotherapy and a separate one for fluidotherapy. I'm dividing this information up though into four lectures. 3 sections on hydrotherapy, 1 section on fluidotherapy. All the slides, however, are in the single PowerPoint. So we'll go ahead and get started. We're going to go through a lot of what we've done with heat and cold. We'll look at the physiological effects and the effects on the body, and we need to, with hydrotherapy, look a little bit at the properties of water that give rise to those physiological effects. We're going to talk about some of the equipment that we use, and we'll talk about different ways that we apply hydrotherapy, and then indications, precautions, and contraindications. And then we're going to finish up with the dosage, in other words, how long, how warm, that kind of thing, and some safety considerations. And then we'll do very quickly dosage and indications, precautions, and contraindications for fluidotherapy. So right now you should have your hydrotherapy lecture notes in front of you. So we're going to start with looking at the physiological effects of water, and we are going to just be talking about these are just the effects of warm whirlpool, and for cold whirlpool, of course, the effects would be the same as cryotherapy. One of the things that we need to understand about water is that it has what we call a high specific heat. Specific heat is how much heat is held, how much heat energy is held per temperature of water. And the other substance that we have used a temperature on has been paraffin. And heat has a higher specific, water has a higher specific heat than paraffin does. In other words, there's more energy per degree. So for paraffin, whereas we can set, what was the temperature that we set at paraffin? Right, 125 to 130 degrees. You would not want to immerse your body parts into water that hot. That would be almost scalding. So we definitely are going to see lower water temperatures. In addition to the higher specific heat, water conducts that heat more rapidly than paraffin. And so it is a good way for us to heat or to cool various aspects of the body. We talked about different ways to transfer heat from one body to another. So what was paraffin and hot pack? They were the same type. They were by conduction. In other words, the body part was touching it. This is going to be primarily convection. Of course, the body part is touching the water, but what really makes it special is that we cause that water to swirl around. So that gives us the convection portion of it, where water is moving around the body part. And you can see up here on the slide the physiological effects. And again, very similar to those from heat or cold. So if we're looking at heat, we have increased temperature, and we'll talk about how the kidney elimination occurs. That you might not have thought of that first off, unless of course you have kids that you've taken to a swimming pool. But if you've sat in a whirlpool, you know that you feel more relaxed, so a little more sleepy. All heat increases metabolism, and if we follow that down, we have arterial dilation, and we know that that's going to increase blood flow. That'll help bring more oxygen and nutrients to the area, and also help us get rid of waste products, and that can definitely facilitate our healing process. With that dilation, there's more pressure in the capillaries, and that can mean that that pressure can push fluid out into the interstitial tissues, which can give us some edema. So that's a precaution that we'll be talking about, is to make sure we're not increasing edema. And then if we go back up to the top, again, if we have full body immersion, we're going to get the systemic effects of heat, because if you think about sitting in a whirlpool, there's really no way for whatever body parts are submerged, they can't cool off through perspiration, so we have a more likely chance of having systemic effects of heat with a whirlpool. So remember that our respiratory rate will increase, heart rate increases, and that's to combat really the effects of the decreased blood pressure that occur because of arterial dilation. So I might have written the arrows a little bit differently, but again, I would refer you back to the other diagrams that we have on the effects of heat in the body. The second principle of water, or hydrotherapy, we're going to talk about is buoyancy. And you've all experienced buoyancy. I'm sure you understand what it means. Things float. And particularly in the body, when we're looking at the effects of buoyancy, what we mean is technically the water is having an upward push on the body. So which way does gravity go? Right, down. So buoyancy is counteracting gravity with an upward force. And we can quantify that force, much like Archimedes did. If we wanted to, we could measure the weight of the water the body displaces, and that would be the force. We're probably not going to do that. But I think this diagram kind of captures that idea that you can diminish the force on the lower extremities in particular by submerging people. So if we stood about waist high in water, a little bit over waist high, we would be limiting the weight that is perceived by the legs by about 50%. If we go up a little bit higher to about chest level, about 25 to 30% of body weight would be felt by the legs. And then if we submerged ourselves all the way up to the neck, and again, I'm sure you've done this if you've walked out into a pool or a lake or the ocean progressively deeper, you know that you start bouncing up a little bit higher with every step, and that's because you're really feeling very little body weight. So you virtually equal the force of gravity the deeper you go. We generally don't treat people up to their necks in water, but it is the principle of buoyancy that's important, and so we definitely use that a lot when we're trying to diminish weight bearing, generally for pain or weakness types of issues. Another principle that's related to buoyancy is called specific gravity. So we had specific heat before. This is different. This is specific gravity. And this has to do with density. Oh, forgot my other slide. So here are, of course, different elements of buoyancy. And this also kind of goes along with specific gravity. So this is just the person floating with their head above water. So again, this would be the situation where 90% of their body weight is really maintained through buoyancy. If we add an air-filled vest, we're basically going to increase the person or decrease this person's specific gravity. In other words, we're going to decrease their density. And then this is a little bit different, saying that the concentration of water, of the salt in the water, increases the density of the water a little bit. But if we go to specific gravity, again, it's density, grams per centimeter cubed, so it's a volume type of measure. Water with nothing in it, so distilled water, is considered our reference substance, and so we give that a specific gravity of 1.0. So anything denser than that is going to sink, and anything less dense than that is going to float. So for example, if we look at some of these items here, we just looked at a person wearing a vest. That might be similar to somebody floating but with air in their lungs. They're going to be a little bit less dense, and so they'll tend to float. And then if we exhale, we become a little more dense and we tend to sink. So I'm sure, again, you've had that experience. You're floating in the water, maybe on your back or your stomach doing the face float. Well, no, I guess you can't inhale and exhale. So let's say you're lying on your back, you're inhaling and exhaling, and as you inhale, you feel your body rise in the water, and as you exhale, you feel your body sink a little bit in the water. Of course, body proportion can play a role in that. People with more subcutaneous tissue may float a little bit better. People with less will be a little more dense. We certainly know that ice is less dense than water, so if you put ice into a glass, it will float. Air is very much less dense, so we use flotation devices filled with air to help us float. And of course, we have different substances like wood or aluminum that we might use in the water, and of course those things have various densities. So again, I'm sure density or the ability of something to float is not new to you. Maybe the term specific gravity is a little bit new. But we use this principle as a way to promote exercise within the water. And so if this person is wearing a flotation vest, that's going to keep them buoyant. So that's going to be using the buoyancy and in our favor. But these foam dumbbells are also buoyant, so when the arm's going up, that's going to be helpful. But when the person's trying to push down into the water, that's going to kind of fight against it. So that'll actually create resistance, and we can see that in this picture. If we're looking at flotation devices, of course, if you did nothing, the buoyancy would cause them to float up, and so that would help exercise in the abduction direction. But if they wanted to work in the downward direction, it would resist adduction. So again, we use the concept of buoyancy and density with different types of objects within the water to help either promote resistance exercises or to assist people in exercising. The next principle I want to talk about is hydrostatic pressure. And again, I'm sure you've all experienced pressure that occurs underwater. It's simply due to the weight of the water again. And the deeper you go, of course, the more weight of water being superimposed on you, and so the pressure is greater. And you've probably dove into water and gone down a little deeper and maybe felt your ears pop a little bit, or like you needed your ears to pop. And so you're experiencing that hydrostatic pressure. If any of you have done any scuba diving, if we were in class, I'd ask you to raise your hand how many people have gone scuba diving, and we'd see how many of you have. But of course, the deeper you dive, then pressure plays a role on the body as well. Now, this law was developed by a guy named Pascal, and he found that when a body's immersed, every single part of the body will be surrounded by pressure that's equal at a given depth. And what this little picture is trying to show you, of course, is that around the entire circumference of the person's trunk here, there's X amount of pressure. But then as we go down to the feet, again, around the entire circumference of the feet, there's equal pressure, but more pressure than is up on the trunk here. So the pressure can have a lot of positive effects, and some of them, again, you might not think about. One thing is that it can make it a little bit harder to make the heart work a little bit harder. So the pressure distally down here actually can promote venous return, and that can be a good thing to try to maybe decrease edema in the legs, but of course it puts more fluid back into the venous circulation, and that's going to make the heart work a little bit harder. So that's one thing to think about. Another effect of putting that fluid back into the bloodstream is that it puts more blood flow through the kidneys, and that produces increased elimination, or in other words, makes you feel like you have to pee. And again, this is the experience everyone with children has had when they've taken them swimming, that they have to get out and go pee. We hope they get out anyway. But we can use this therapeutically as a way to diminish edema through promotion of kidney elimination and activity and elimination. And then a potential negative effect of this pressure is that it can put force on the chest wall externally, making it more difficult to take an inhalation. In other words, to inhale, and so that can increase the work of breathing a little bit. So just something for us to think about. If we have someone with their chest submerged, their heart's going to have to work a little harder. It's going to be a little harder to breathe as well. All right, that's it for hydrostatic pressure. I'm going to change topics here again and talk about another principle of water, which is that there is cohesion. There is cohesion between the molecules of every element of matter. We just notice it a lot more when we are dealing with a solid, like a table. The reason you can knock on a table is because the molecules of the table are adhered together. They have a lot of cohesion, so your hand doesn't go through the table when you pound on it, unless you pound really hard, I guess. With water, of course, as a liquid, there still is a tendency of cohesion, but yet we can push through it much more easily. So that cohesion gives us some of the resistance. And again, I'm sure you've had the experience of you are walking maybe, shin high or knee high in the water. And if you go slow, it's not so hard, but then as you try to increase your walking speed, it actually gets more difficult. And so that's what you're seeing here, is that there's actually more, the faster you try to swim or move through water, the more resistance that you actually will meet. Kind of a special case of cohesion is what we call surface tension. And so that tendency for those molecules to stick together is greater on the surface than it actually is underneath the surface. And you might have seen this if you've ever done this little experiment. If you haven't, I urge you to. So for one thing, you just look at that cup of water and you can get a sense that the water is kind of a little bit above the rim of the cup. And so if you fill up go to the cupboard when you go in the lab later, take a little Dixie cup and fill it up, and you'll see that you can fill it up slightly over the top of the rim. Then if you very gently take a paper clip, which if you look at its specific gravity, should not be able to float, it should sink, it will float on the surface of the water. It's very fun if you haven't tried it. And then if you just push on that paper clip, it will sink rapidly to the bottom because you've broken through the surface tension. Another example of that is, I'm sure you've seen bugs skittering along the top of the water, and that is not just because they're such great swimmers, but they are taking advantage of surface tension. So the implication for us is if we have people exercise and their arms are or their legs are kind of moving, skimming along the surface, the cohesion there is slightly greater and they'll be working slightly harder than if they were actually underwater. And then finally, the last principle we're going to talk about is turbulence. And this is a stream in Glacier National Park. So this is caused by movement, high velocity movement of water creates turbulence. And we can again use this to resist exercise, but we also can use it for things like wound cleansing. And we'll talk about that more when we get to the part where we're talking about indications of hydrotherapy. So in summary, this slide will just give you some of the properties on the right-hand side, the thermal properties, buoyancy, pressure, surface tension, cohesion, turbulence, and then some of the purposes or the things that we can use them for. And so you can also couple this with some of the indications we're going to talk about in the next section. So I thank you, and I look forward to talking with you again in the next section.